session. All right, today what we'll discuss is we'll continue the transmission line parameters. So this is the last part in the transmission line parameters on chapter 4, and this is about capacitance. We discussed the resistance, conductance, inductance, and today is the capacitance of transmission line, how to determine the capacitance. Now, when we talk about capacitance, we talk about electric field. When we talk about inductance, we talk about what? I want to hear from you. Talk about what? Inductance.
Magnetic field.
Magnetic field. Very good. Okay. So therefore, we need to use to have the voltage between two conductors or between the conductors. So the capacitance from charge per unit is, as you know, this is the charge over the voltage. Give you the capacitance. Therefore, we need to integrate or the charge. We need to. So this is how we drive our thinking now. So to do with charge and voltage. To find the capacitance, we need to do with charge and voltage. Therefore, we need to find the charge. We need to find the electric field. The electric field is simply what is the charge Q over 2 pi epsilon x. X is the distance between, for example, 2 points. The distance between 2 points, P1 and P2. Epsilon here is called permittivity. In inductance, it's called permeability, samahiyah. Both are the same meaning in Arabic, samahiyah. So in capacitance, we call it permittivity. And as you can see, we integrate outside the conductor. So the electric field will be pronounced like this, okay? In the magnetic field, it's a loop. It's around. That's why we do around the loop integration, surface integration, loop, closed integration, closed loop. And this is a charge is just from positive to negative. Okay. Therefore, we want to have the voltage. The voltage is simply the integration of the electric field. So we want to find the voltage is simply the integration of the electric field. So to do that, from where to where? From D1 to D2. Integration of the electric field from D1 to D2. Therefore, we can put the electric field in this form, as you can see, in this form. Then when you see now what we are integrating, actually, we're integrating with respect to what? With respect to the distance here, x, which is D1 from D1 to D2. This is x. X is greater than the radius and with 1 meter length, x. Okay, so this is what integrating x. Therefore, when you see x is in the denominator, then it will come to your mind, we should put what? The natural log, because 1 over x, integration of 1 over x. And this is simply d2 over d1. Okay, d2 over d1. Okay, that's why we get the natural log. Just to understand, because you are engineers and you need to know the theory behind these. Okay, so simply that we can determine the voltage Ki between conductors K and between conductors I. Due to what this voltage is due to conductor M, due to the charge in conductor M. So we have a voltage due to conductor M, and when we talk about a voltage, we talk about electric field. So we know the voltage is the integration of the electric field. So okay, so there is a charge in conductor M. How it will affect the conductor K and I, or the voltage between conductor K and I. So this is the formula, as you can see. And if we use the superposition for a number of conductors, we get these simply. Okay, we're just adding the charges and natural log dim, dkm, etc. Because we have a number of conductors. We just do superposition. We are adding them. And we can go on and determine the capacitance of single phase. When you hear single phase, it's a two-wire line. One is go, one is return. Therefore, we just can add them. dyx over dxx. This negative here, because we can put this at the top, dyy, and this is at the denominator. So we can put the negative here. That's why we have negative. Okay. We can have positive. We put it this way. Okay. So we put it like this: dyx over dyy. Okay. So we can put them as negative. Why we put them as a negative? Because we want it to be in this form. We want to be in this form here. So we can just have natural log dyx times dxy. dyx times dxy. So the y dxy is like this. Over dxx dyy. What's dxx and dyy? Is the geometric mean radius of x and geometric mean radius of y. This is it. Or the radius. In this sense, in this case, we have only one conductor, so it is the radius. Remember now, it's the radius of the conductor, not r prime. We use r prime 0.7788 times the radius, that's r prime, in the inductance. In the inductance. Here we use the radius. Okay, so for the capacitance, we use the radius. This is the difference, one of the differences when you calculate inductance and when you calculate the capacitance. And then we can put it just in this form. The voltage will be this form here. So it is natural log d, the distance between the conductor x and conductor y, over radius of x times the radius of y. If radius of x equals radius of y, therefore we can put them, we can just put rx or just r. Okay, so this is the natural log of the geometric mean distance over geometric mean radius when we talk about bundle conductors. From the voltage, we can determine the capacitance. This is our goal here, to determine the capacitance. And this capacitance is simply Q over Vxy. Therefore, we can put it in this form. Okay. We can put it in this form here. And we say line to line capacitance also can be measured as line to line. Why? Because we are saying Vxy. When we say Vxy, it's line to line from conductor X to conductor Y. Although this is a single phase, we say line to line. So it's from conductor X to conductor Y. Cxy, it means the capacitance between the two lines. Cx, neutral, so it will be, or C neutral, so that will be just from the wire to earth. That's a capacitance between wire and earth, and the capacitance between wire and wire, or conductor to conductor. Okay, so therefore Cxy is simply y times epsilon, which is the permittivity constant, over d over r, the natural log. This is farad per meter. Again, now we're talking about it's farad per meter. It's like Henry per meter. And then that's it. So this is, we can determine also regarding the neutral. We just multiply by 2. Multiply by 2. So the C neutral is C times Cxy. Where we get this one? Here we get it like this: Cxn equals Cyn. So therefore, it will be 2Cxy. So therefore, the neutral, the capacitance to neutral is double the capacitance from line to line. Okay. The capacitance to neutral is higher than capacitance line to line. Okay, so that's why then you will have 2 here. Don't forget the 2, because you are measuring what? You are measuring the from the conductor to neutral, from the line to neutral. Therefore, you will put 2. If you are from line to line, there is no 2 in this. No 2. Okay, same, exactly the same equation. It's just there is no 2. We just multiply by 2. Therefore, we get the capacitance to neutral. And again, it's farad per meter. It's farad. Farad is very large unit. That's why you measure capacitors in microfarad, in millifarad, in nanofarad. So farad is very high unit, a very large unit. All right, okay, so that is to bio natural law. Now we go to our favorite bundle conductors, and then we can just add them. VAB, for example, VAC, we can go all the way here, VAB, what is VAB, QA, etc. So for each conductor here, B and C, we have 3 phases. Now, by the way, this is a phase, huh? It's not bundle conductor, but these are phases, A, B, C. Okay, it could be bundle conductor, it could be phases. In this case, what you see here is 3-phase line, equal phase spacing. So they are equal. But it's hard to have a tower like this. It's very expensive. So the towers mainly does not look like this. As we mentioned, the towers will look like this. Okay, so we have it like this, and then another one here, and then you go down, and then maybe another one there, like this. So this is so therefore the phase B, phase A, phase C, they are not equal phase spacing. They are not unequal phase spacing. And this is the easy to construct a tower like this. Okay. But it's difficult to have a tower that has one up, and it becomes more expensive. Therefore, we don't have towers like these. Okay. Okay, but it's just an introduction to you to do what's equal phase spacing. So to know if they are equal, we're simply what we do here, we're just adding the voltage. We add the charges here, natural log, etc. for the phase B and phase C. And then we can go on DAA equals DAB, or DAA equals DBB equals the radius. And all the distances are equal the same, which is equals D. Therefore, we can put the form into VAB will be this one here, VAC will be this one. Okay, it's just same. Just change what QC, QA, and this is QB, QA. No problem. Okay, this is just adding them. And then what we want actually to do, we want to determine this at the end. So we can go on and determine what we are doing here. Okay, changing or simplifying the equation until we come to this equation here. Okay, so this equation here, line to neutral, this is the one that you will put on your cheat sheet in the final exam. Okay, I will not ask you about the derivation. Okay, but as an engineer, you need to know the theory behind why we have a natural log. So you already know natural log because we integrated 1 over the x and CAN and CAB, for example, conductor. So this is the capacitance of neutral, of the capacitance to neutral per line, the line to neutral per line length. And this is per line length is as mentioned here, farad per meter. If the line length is 200 kilometers, then you multiply by 200 simply. It give you farad. Okay, R is the radius of the conductor. D is the distance between each conductor. So therefore, the capacitance to neutral is CAN for one phase, and the second phase will be the same, third phase will be the same, because they have equal phase spacing. When they do not have when they have unequal phase spacing, what we do transposition. Okay, we do transposition. Therefore, we can neglect the unequal phase spacing because it will not be accumulated as the line continues, as the line length increases. Okay, so we do transposition. Here, what we do here, they are also similar to what we discussed in inductance, when we calculate the inductance. So we want, what is the difference here? The difference here is R. We use R. So the geometric mean radius is simply we use R. And I want you to see now, this is what. All right. Okay, so this is R. And then the DAB, DAC, there we can't have it like this. But at the end, we come up to this line here. This is your result. The equivalent over DSC. SC means this is the radius of the capacitance. Okay, regarding capacitance, DSL is the radius or geometric mean radius of the inductance. DSC is the geometric mean radius of when we calculate the capacitance. Geometric mean radius. Why? Because there is a difference between geometric mean radius in calculating the capacitance and geometric mean radius when calculating the inductance. What's the difference? It's R. We call it R in the capacitance. We call it R prime in the inductance. Less. Okay. It's less R prime, 0.7788 times R. Therefore, but the equivalent will be the same. So if you're asked to find the inductance and capacitance, you will only calculate the equivalent distance, which is the equivalent, which is geometric mean distance, once, only one. Okay, once. While the geometric mean radius, you calculate it for the capacitance and you calculate it for the inductance, different. But same category here, same thing here. You will use it exactly the same formula that we discussed. It's just this is instead of R prime will be R. That's the whole difference between inductance and capacitance regarding the geometric mean radius. So this is your equation that you will use in determining the capacitance. If you want, now what does the capacitance do in the transmission line? The capacitance charging currents. So there is a current flowing into the line. That is reactive power. Okay, so there is a reactive power. Reactive power flows into the line. While in the inductance, reactive power flows, it's leakage reactive power. Here it's charging, it's injecting reactive power. Capacitance inject reactive power into transmission line. Inductance draw reactive power, absorb reactive power. So we wish to have capacitance on the line, because it will relieve and improve, it will improve the power factor. Why we improve the power factor? The power factor usually is lagging. Why it's lagging? Because you are dealing with industry. Industry uses reactive power because they run with motors. You use also in housing. Also you use commercial. You use AC or the air conditions. These are motors, so they are absorbing reactive power. So the normal load is inductive. Seldom to see in the capacitive load. Where will we see capacitive load unless we have a charging current? Okay, so the normal load, physical load, is reactive power is lagging. Therefore, that's why we use capacitors. We use capacitor to inject reactive power, and we like the transmission line to inject reactive power. So we want the capacitance to be high and the inductance to be low in the transmission line. All right. Therefore, we can have what we can determine what is Q. Q is simply Q for your three phase will be Q for three times the single phase. So this will be 3. After we find the capacitance, you multiply by 3 times omega. So we know what's 3. 3 is the 3 phases. Okay, 3 phases, and multiply by V square line to neutral. Or you take rid of the 3 and you multiply by V line to line square. Why? Because V line to line equals square root of 3 times V line to neutral. So therefore, V line square root of 3 squared will be 3. Okay. So therefore, 3 over 3 will cancel. Okay. So therefore, we can have line to line. Okay, line to line. So please remember these 3 for 3 phase. But it depends on what you want to do. You want line to line to use it, you can use it directly for what? For 3 phase now. We're talking about 3 phase. You do it like this. If you want it only for single phase, you cannot use a line to line, you can only use a line to neutral. Okay, line to neutral. Okay, 3 phase, you simply put line to line at the same equation here. Same equation, just compare between these 2 equations of, or you put it this way and multiply by 3. Simple, very simple. Okay. Another thing here, we can go on with the same thing that we did in inductance. What we do, we want a single phase and blah blah determine the line to line capacitance in farad. So in farad, when we talk about farad, then it must give you what? It should give you the distance in farad per meter. So it should give you the distance. So where is the distance here? Will be here 20 miles. Okay, so this is not okay. So farad, so you multiply by 20 miles. Okay, so the same thing here. You will go to table A3. Why is we go to table A3? Because table A3, we go a single phase. Here we go. Now, this is referring to what? To example 4.3. So I wrote example 4.3 here. 2-stranded copper conductor. So we use this one, 12 strand 4/0 copper conductors. Okay, copper conductors. Here we are. So therefore, you will go to table A3. In the final exam, you will be given table A3 and table A4. And we'll give you, so from, if it's copper, you will go to table A3. Will not ask me what table I will use. So please focus on this. I will still have students, they ask things, maybe they are not drawing attention to the class, to the lecture. So please, if you cannot draw attention to it, then you need to listen to the lecture again. Okay, so I will not answer questions that whether I will use table A3. You will not be asked to use table. We'll just give you to find the capacitance, to find the inductance. Then you will determine what table you will use. Okay, so in calculating the inductance and the resistance, we simply just go to table A3 as we did in the inductance. We know how to, and then you will find this one in inches. You will find what? You will find the geometric mean radius. Geometric mean distance. Okay, the diameter, not the metric mean distance, the diameter. Then you will divide diameter by 2. The diameter is in inches. Given in inches, the diameter of this line here. Okay, of the copper 12 strand in table A3. You will divide by 3, and then you can change it into feet. It's up to you now what to do. You want to change it into feet, you want to change it into meter. How do I, what to change? The change depends on here, what you are going to do here. With this one, 5 what? 5 feet or 5 meter. If it's 5 meter, therefore you need to change this into meters. Okay, then you will put 5 meters. Here is written 5 feet. 5 feet. Therefore, you will put 5, the natural geometric mean distance between two conductors. This is a single phase. Between conductor X and conductor Y, the distance is 5 feet. Therefore, simply you will get CXY line to line. CXY line to line. Okay? And then you will just multiply by 20 miles. Remember now, this is farad per meter. Farad per meter, the given is miles. Therefore, we convert miles into meter. Here we are. These simple things that you are required to do it. So please don't tell me that you forgot or to change from mile to meter. You need to focus on what you're doing as an engineer. You will be given these before you give it to the data entry. Data entry staff will enter the data in the software. Okay. We'll enter the data, the X, the R, the Y, the X, the R, the transformer data, the transmission line data. Okay. Not an engineer. The engineer will work on these and then prepare the data. Anyone can do this. Your assistant, as an engineer, your assistant can enter the data in the software, and then you will have the analysis, and then they run and they give it to you as an engineer. Then you will read this, and then you can determine what to do. Okay, when you read the voltage profile of the system, the transmission flows. Okay, that I'm talking about load flow software, for example. Okay, but you need to prepare the X and Y, the X, the R, the X, the C. That's what you put for the transmission line, and for the inductance in per unit, you put it in per unit. Therefore, all these done offline. Okay, so you already know the distance between a city and another city. So with the transmission line. Okay, so therefore you will get these. This is in farad. Y, this is the Y, XY. So this is the admittance. Admittance is simply J omega times C. Okay, admittance. It's like omega L in the inductance, omega 2 pi F. So therefore we can write just 2 pi F times this one will give you the admittance, shunt admittance Y, which is capacitance. And this is still line to line. We want to find the reactive power from this capacitance here. Is simply we use C multiplied by 20 times 10 to the power of 3 watt voltage. Talking about 20 kV. Here we are in this here, 20 kV. So 20,000 V line to line. By the way, if you're given a 3-phase and your like this here one, if the line voltage is 20 kV, for example, this is giving you now line voltage is 20 kV. You will, okay. So therefore, it's the line voltage. It means from line to line. Okay, so this is give you for the this is a single phase, by the way. It's a single phase, so it's not even 3-phase. But it's if it's a 3-phase, we don't tell you this is a 3-phase. It's a called line to this means line to line. Okay, so this is a single phase. So just multiply by square root of line to neutral or line to line. It's a single phase. Okay, so not three phase. So it's a square root of 3. So that is what you will get kilovar. So so what does it mean now? It means that the transmission line, which is made of this copper conductor here, this transmission line for 20 miles, produces this much reactive power, 25.1 kilowatt. It produces the line. So this is the injection of the reactive power. Or you can, what you do, or you can put, if you are in the data entry, okay, if you want to set your data, you will put this one here as 1.66 farad in farad. Or you will put it as Y. You don't put it in farad in load flow, so you will put this one here. 6.27 times 10 to the power minus 5. Siemens. S معناها Siemens. Okay. When we talk about the admittance. Okay, it will be the same thing here. We will not repeat ourselves here. Here, when it comes to three phase, it's simply what we do here in three phase line. And you see now, if the line voltage is, this is what I'm referring to. If the line, it will not tell you, although in the exam I gave you the three phase, etc., in a parenthesis to make sure that you understand this three phase. But in this, if the line voltage is 345, you will not ask, is it single phase or three phase, line to line or line to neutral? It is line to line. Why is line to line? It's written here if the line voltage, and we're talking about here is a three phase. So they will not put in a parenthesis for you, it is three phase voltage. It will say 11 kV will be three phase. Okay. But for in the last exam, I put this in parentheses to make sure this is line to line voltage. But when you read the textbook, you will not find this in parentheses. Okay, line to line voltage, and you're talking about three phase. That's it. So it is line to line, not line to neutral. Determine the charging current in kilo ampere. Determine the charging current in kilo ampere per phase, and the total reactive power in megavar. Okay, megavar. Some of you are asking megavar, how much kilo? 1,000 kilovar is 1 megavar. So this is 1,000 kilovar supplied by the line capacitance. Okay. All right, so you go to table A4. Now, why we go to table A4 again? Because it's written ACSR. Okay, three-phase example. Okay, this is ACSR. You see this example here is referring to this example. 4.7 referring to 4.5. This is in your textbook. Therefore, it gives you in 4.5 all the details of the conductor. Therefore, you go to table A4 and simply do the same thing. Will not do anything. And then geometric mean distance, or geometric mean, this is what DSC is, the geometric mean radius of the conductor. Same thing that we mentioned in, that we discussed in the inductance, except this one here is, we put it exactly the same now, the radius, not R prime. Okay, so this is the geometric mean radius. This is R. All right, so we convert it into meter because the distance now is 0.40, 0.40, which is here. 0.40, it's written as the distance, geometric mean between these two. This is about 40. Okay. And then you will find the DSC. Therefore, you can find the capacitance as we mentioned before, how to find the capacitance in farad per meter. In farad, you find it in farad per meter first, and then multiply by what is in kilometer. Okay, you want 200 kilometer. 200 kilometer, therefore, you multiply by 200,000. 200,000 to give you, this is in farad. You see now in farad, it's 10 to the power of minus 6. Farad is very large. The unit, it's not 2.17 farad. So please, when you write this, makes sense. When all the numbers you write in any course, does this number make sense or not? If you write 2.17, this is too much. You cannot say that I forgot to turn by, because it does not make sense. Okay. Too much is 2.17 farad. So 2.17 times 10. So this is microfarad. Okay, this is microfarad. 2.17 microfarad. So please, when you write these, make sure that you do it as, does it make sense? Does it make sense is one of the skills of engineering, by the way. Does the number make sense or not? This is one of the skills of engineering. Okay, when they review their data, does the number make sense or not? And then we just go on and simply multiply. You see now how things become in power. You repeat whatever we discussed in inductance. We repeat it now in capacitance with minor changes. In capacitance, we're looking for the I charging current. You see, we did not discuss I charging current in the capacitance, in the inductance. It does not charge, it's just absorbing reactive power. Here, charging reactive power. So charging reactive power, that means what? The charging reactive, V times Y. So we know V, we know Y, and we know V. The voltage is given, and the Y, we determined Y, therefore, which is V over Z. I is V over Z, means V times Y. 1 over Z is Y. Is the admittance. 1 over impedance equals admittance. So you multiply admittance times the voltage, give you the current. So what is the voltage? This is line to neutral. Again now, maybe this is the best way sometimes. You just make it line to neutral, and then whatever you want, you multiply by 3. So line to neutral, and this is a line to neutral also. Let's see. Okay, then you will put it what? You will just multiply this one, and this is a line to neutral. Don't forget the square root of 3, because this is what's given line to line. Okay, 3 phase, line to line, and this is giving you 0.16, which is 163 ampere. Okay, 163 ampere. By the way, the transmission line takes about 4,000 ampere, 5,000 ampere. On the transmission line, that's what you see on the road. Okay, so the current there is about 5,000, 4,000 ampere. Okay, so the kilovar here is 97.5 megavar. And this is what for the 3 phase now. For the 3 phase. How do we know? We know it from here. So you know this is the charging, the admittance here times the V line to line. V line to line square times Y. Okay, give you 97.5 megabar for 3 phase. Here we're talking about I charging. When you see I charging, you need to multiply. You need for single phase. You cannot add phase A, phase B, phase C. The current we don't add. If we add, the current will become zero. Okay. For phase A plus phase B plus phase C, if we add them, it will be zero, as you know, in the neutral. I neutral will be, so you do not add the current. So you say 3 phase, then you multiply this by 3. You don't do that. Okay, this is ampere per phase. That's it. So you leave it. It's per phase. So you don't add the 3 phases there. Okay, so per phase, so we know the other phases will have the same magnitude but different angle, 120-degree angle. Okay, so this is the magnitude. I charge per phase. I'm talking about the phases itself. Okay, so this is charging per phase. I'm talking about the phases, not the charging. Huh? The charging current will be 0.163 in phase A, also charging to phase B, and also charging to phase C. Okay, this is okay. But to calculate the current on the phase, that's what I was discussing. Current on the phase. Okay, so in here, okay. All right, so this is just table A3 as we discussed before, and this is the beauty that we discussed also in the table A4. All right, now, okay, any question here regarding this one before I move to the second part of this session? Any question?